Now?
Can you hear me?
And at this pitch also. Now? Yeah, it's okay. All right, so let's get started. Hi, my name is Nakul, and today I'm going to speak about distributed tracing, a very important tool that helps to debug and understand distributed system and microservices. So if you are building distributed systems or microservices, then this tool can help you, or this concept can help you to address some difficult and hard to reproduce problems such as long-tail latency. I would like to kick off this talk by discussing why even we should bother about latency and what role it plays in distributed systems. After that, we will take a look on what distributed tracing can offer us. Next, there will be a short demo just to get a feel about distributed tracing. And after that, I will like to show you what is Zipkin and how we can benefit by using it in our tech stack. And finally, I would like to walk you through the code that is used by the demo application. So, what is latency? Well, one may define it in simple words as the amount of time it takes to complete a task. So for instance, let's say I want to fly from city A to city B, and it takes 4 hours. So in this case, my latency is going to be 4 hours. Some people tend to mix throughput and latency and believe that improving the throughput is also going to improve their latency. Well, it's not the case really. So coming back to my example of flying from city A to city B, improving the throughput means instead of flying 1 plane, let's fly 5 planes. So now we can carry more passengers from city A to city B. However, the latency, that is overall time for every passenger, still remains the same. In programming, whatever we do takes some amount of time. Every operation, for instance, if we want to access L2 cache, it takes time acquiring mutex, acquiring lock, unlock, disk seek, access to the main memory reference. They all take some amount of time. Maybe the amount is so small that it is negligible. However, if we are hit with a huge scale, then all those small numbers starts to add up. You will say, well, who really cares about latency after all? It's not hard to guess that it's the end user who suffers the most. But the funny thing is that they are not sitting with a stopwatch and counting how long your application takes to respond. On the contrary, they are just driven by some needs and they want your application to finish that task. However, in some case, speed is the name of the game. So for example, in a trading system, low latency can make a difference between grabbing an opportunity and losing an opportunity. The users really don't care how fast your application responds, but they do start to care when things starts to get slower. So what makes distributed systems so interesting? Well, in a distributed system, a single request may end up touching hundreds of services written in different programming languages and deployed using different various runtime and probably deployed across many machines. In a monolithic world, we can somehow squeeze all that picture in our head by using some diagrams, some documentation, you name them. However, in microservice world, the picture is ever changing. New service can spin up in matter of days or week. Old services can be replaced. We can have some services which need to be upgraded because of performance related issue. So it's really impossible to keep all that information in the head. And what happens when all of a sudden things starts to get slow? Well, it's difficult to pinpoint what can be the cause. Maybe it's a new service, maybe it was the old service, or maybe it was some upgrade that happened during between. So now I'm going to tell you a short story about Bob and how Bob encountered a long-tail latency issue. So Bob is a programmer and he just migrated their legacy application to microservice application in order to address the business needs. However, he started receiving some random emails from the customer complaining that their system is working really slowly. Since there can be many sources of potential errors like slow disk I/O, networking errors, maybe GC garbage collection was kicking in somewhere in between, or some slow queries. Bob had really no idea where to begin, even start looking for the problems, let alone to search a solution. Bob didn't know that time that he was suffering from long-tail latency, but he tried his level best to troubleshoot those problems. So first option which he tried was log analysis. Since there were a large number of, lots of services were there, it added up having lots and lots of log files. When he started to dig up in the log files, he found an overwhelming amount of information. There was a lot of noise like thread dumps, asynchronous stack trace, so on and so forth. Moreover, not everything was in critical path because some of the services were just asynchronous by nature. So when they receive the request, they immediately respond, okay, and spin up some background process. So in reality, they were not the cause of the problem, or they can't contribute in causing those issues. Moreover, correlating all those logs requires some manual efforts. At the end, Bob ended up with some bunch of numbers and what to do with those numbers. One option was to take maybe mean, maybe mode, maybe average, standard deviation, what to do with them. So in a nutshell, all those numbers and that log analysis simply doesn't help him to resolve those issues. So the second option was to go and ask for matrix to help. Well, matrix can tell that something is wrong. However, it can't tell the cause. What is the cause that caused this problem? Furthermore, the way in which we aggregate this data can give us some false positives. So, for example, let's say there is a country where 100,000 people are living, and one person is making $1 billion a month, and others are making only $1 a month. And if we take the average of this, we will say, well, everyone is happy in that country, basing on the income, but that's far away from the reality. So Bob started to wonder whether it's possible to find out how many clients were impacted by this problem. That's where Bob started to learn about percentiles. So he was precisely interested in the 99th percentile of his system. So the 99th percentile just simply means that 1 out of every 100 visits experience some delay, D. And in our case, this delay can be 50 milliseconds. So the total visits that were experiencing the delay can be easily calculated by using n, which is the number of visits divided by 100. So right now, as you can see, this number is really not so alarming. It's 5,000 out of 500,000. However, we were in distributed system. So a single visit by a client was resulting in making 8 downstream calls. And those downstream calls were interacting with some highly active service, which was 99% fast but 1% slow. And now when we start to take into this consideration, then the likelihood of encountering latency during a single visit was 1 minus 0.99, because 99% is 0.99 expressed here, to the power of number of downstream calls. So it is 8 in our case. And after doing the maths, it ends up to 8%. Now, the total visits affected can be calculated using 8% of n. So this number. Now you can see it is 40,000. These are lots of visits. And moreover, this number is directly dependable on the number of downstream calls. So if we will have here, instead of 8, in future 20, then this number will be different. And interesting thing to notice is that it can affect probably every customer in our domain. Why? Because usually a customer visit, let's say, the website a few times in a day. So there exists a likelihood that all the customers will notice those latency-related issues. So Bob was happy to find out that there is some small progress. However, when he went to the boss really needed a solution to address this problem. But the Bob still didn't know the request timeline. That is, when the problem was started, how many services were involved, which operation were involved, and how many of them were in the call graph. How many of them were in the critical path. Also, he didn't know how to correlate the log, and moreover, he did have no possibility to kind of test whether the single request is really slow on various cluster, or it is only slow, I don't know, in east zone but not on the west zone. He didn't have all those data really to work with, which could help him. Moreover, he didn't have any clue how much they are deviated comparing to the acceptable value that the delays were. And last but not the least, he didn't know the call graph. So how a particular call, a request traveled in his system. So in a nutshell, he was missing distributed tracing. So what distributed tracing can help or does for us, it can first track some request flow. Which means that when a single request flows through our system, it can track how that request propagated in our system. And this data is usually available within minutes, so we can react really fast. Moreover, the apps can be dynamically instrumented, so it means we don't have to go and write some special code in order to make it work. And it can provide us some great benefits, like which services were involved, which operations were invoked, at what time, so on and so forth. So we can say them like some system insight. It helps us to measure the end-to-end latency, and last but not the least, we can use distributed tracing to perform some sort of optimization, like spotting redundant requests, or maybe some calls were supposed to be executed asynchronous, but they were executed synchronously. And I will show you this during the demo. So now the question comes in our mind, how can we apply this knowledge, which we already discussed? Well, the answer is simple. We can use a tracing system. A tracing system should be able to obviously trace, and when I mean trace, I don't mean that it should trace only across particular clusters or nodes. It should be able to trace across various programming languages and which are potentially using different runtime environment. Also, it should have low overhead, because we don't want to bring our production down because we are tracing something in our production. It should be scalable, because it should be able to handle as our business grows and our services grows. It should work round the clock, 365 days, because production bugs are difficult to reproduce, and it shouldn't rely on programmers' collaboration, because if it will make it too fragile, and then the whole concept of tracing is not going to perform so good for us. OpenZipkin is an open source tracing system. It is developed by, so initially it was called Zipkin, and Zipkin is a distributed tracing system. It is created by Twitter, and it is based on Dapper. And OpenZipkin is more like a GitHub organization. So they take the primary fork of Zipkin and remove the bits which were specific to the Twitter, so every one of us can access it. It's open source, and super important is the pluggable architecture. So we can plug the type of storages depending on our competence of the team. One thing which we should learn before diving deep into Zipkin is about span. So a span denotes a logical unit of work done. It have a start time and an end time. So the work done is expressed in human-readable string. For example, create catalog, calculate cost, foo bar. They are the operation names. They are created by Tracer, and Tracer is this instrumented code which runs in your application and generate all those spans. And they are super slim, so they just carry the bare essential information. And also the root span, that is the span, initial span that is created, it is a span without a parent ID. So after knowing what a span is, let's take a look on how the Zipkin annotation works. So we have a client who makes an HTTP request to get something, in our case, catalog, but it really doesn't matter. So it marks the beginning of the span, so the span gets started here. After some time, the server receives the request, and now we can calculate the network latency by using SR, that is the time at which the server received the request, minus CS, the time at which the client sent the request. So this is going to be our network latency. After some time, the server is done with the processing, and the processing time can be calculated using SS, which means server sent, minus SR, which means server received. Then the server hands the response back to the client receives the response, it marks the end of the span, and the network latency can be calculated using CR minus SS, which means client received the time minus server sent the times. And the overall response time can be calculated using CR minus CS. So CR means the client receive and CS means the client send. So this time minus this time can give us the overall response time. However, if we go deep in this HTTP request, what happens here, we can notice something, that when we call the get catalog, what the catalog service does is it asks some price service to fetch the price, and then it calls some another service, product service, which call some database call. It makes call to some data analytics service, and finally hand out the response to the client. All these green boxes which you see are span, and the collection of this span is what we refer to as trace. One thing which is important here to notice is when we created, or when the Zipkin created the initial span, there are some, let's say, some small fields which are associated with every span. So first is trace ID. The trace ID remains the same for all the span. And as you can see, it is 1 here and 1 here. In reality, just to fit this number on the slide, I have chosen 1, but in reality, it is 64-bit or 128-bit of randomness. So they are unique. And why 64 and 128? Because it depends on the version of Zipkin. Previous was 64, and now they support 128-bit because of the collision in the IDs. Important thing is the Zipkin takes care of linking a particular span to its parent using parent ID. So as you can see, this and this span have the parent ID of 1. So this is the span ID of this becomes the parent ID of this. And for every span, it generates a new span ID. And here you can see the parent ID of these two span is this, 3, because Zipkin takes care. So this is how it handles about spans. So what is a trace? A trace is a DAG, which is directed acyclic graph of spans, and it forms a latency tree. So now I will like to take some time to show you a small demo application so that we can move forward. The code of the demo application is available on GitHub, so you can fiddle around after the presentation. All right. Excellent. All right. So, shall I make it bigger? Now can everyone see it? All right. So what I am doing right now is I'm making a request. I make some request, GET request, to some service running on port 8060. And it gave me some bunch of JSON here. But the interesting thing is, right now I haven't told you anything about this application, what this application does, what this demo application is all about. So let's go to Zipkin and ask whether it can help us. All right. So first of all, I would like to know what this application does in reality. So this diagram is generated all by Zipkin. I can make it bigger so you can see it much better. So what this application does is it have a bunch of services. One is called price service. It is used by catalog service. One is product service, which is used by, again, catalog service, and it uses Apache Spark and Mongo. And these two services are used by this particular service, which is called product service. So right now I have some fair bit of idea what parts of the what the sample demo application consists of. Now if I can say some find trace, I can see here the trace what happened when I make an HTTP GET request. So bunch of spans get generated here. I will make it like this maybe. So I can expand here all. So what happens is when I issue a request to a catalog service, I made an HTTP request, which in turn is called create catalog. And during create catalog, I fetch the price, product, and email. And all this information is gathered by Zipkin here. After that, I can see which class it was and which method was invoked. And even I can see that I'm using a circuit breaker here, Hystrix, and which threads were involved here, and on what was the local address on which this service was running. After that, the create catalog service calls some price service. Again, it makes some HTTP request, and the price gets calculated by another service. And finally, it calls some product service, and then it makes another HTTP request, and during product assembly, I retrieve the product and I filter the products. And finally, there is some asynchronous operation that takes place in the background. And all this graph is generated by Zipkin by itself. So at this very time, I know what happened in my system, and even can go to Zipkin and ask for some more things here. But let's say if I make another request here, going back to my... So let's say I make another request here to some other product, and I see that this product takes some time. I can go to Zipkin and ask again whether it received some data, and instead of long as first, so we can sort it by new as first, and for sure it received. And if I expand them all, I can see that the price calculation have some cache miss. So I can click here and I can see that the cache was missed, and the calculation took 30 seconds, and on which cluster the request got executed. What is more nice when it comes to Zipkin is, let's say if you have a lot of requests, you can go to Zipkin and ask for all the requests which have the cache miss, for instance, happen during it. So if you are running it on production and you face some sort of a problem, then you can go to Zipkin and query the traces using this information. All right. You can also do here in Zipkin, again, just to show you what Zipkin is capable of. We can also highlight trace based on the errors. So if you get some error during processing some of your requests, maybe you can decide what an error condition is. Maybe the database queries take too long, or maybe the cache was missed, so on and so forth. The Zipkin can highlight all those queries. So in this case, I executed some Mongo query, and I encountered some problem while fetching the products. What more we can do is we can ask Zipkin about all the services, and this information can be fetched via either command line, or you can go and see in the drop-down section here. Zipkin also allows you to fetch some information about which version it is running here using this endpoint. And finally, all this information which we see, which I've shown you, is also available if we want to use purely, I don't know, some machine learning algorithm to process those. So it provides some API endpoint, and we can fetch all those information. And as you can see, just using some JSON and parsing relevant bit of information, I created the same tree what was represented on in the browser. So coming back to the slides, let's try to understand the architecture of Zipkin, how it really works. So we have some service in which some instrumented code is running, and this code creates some spans, and those spans got transported via Scribe, Kafka, or HTTP, and the collector receives those spans, and storage sort of deserialize, sample, and schedule them for storing. It can use under the hood Cassandra, MySQL, or Elasticsearch to store. The API, the service which I shown you on the command prompt, it uses the storage to retrieve the data, and the UI in the browser which you see, it is just a part which visualizes this data. So this is how internally the Zipkin works. What is a tag? A tag is an important concept in Zipkin. It denotes some key value pair. This information is useful when you want to kind of understand some context with your request. Like in my case, it could be a calculation time when the cache was missed. It can help me also during debugging this information. Also, we can have some sort of tags. This is like what was the class which was invoked, what was the method it was executed, so on and so forth. The log denotes some really meaningful movement in the lifetime of a span. This info is time-stamped, and a span may contain 0 or more logs. In our case, it was products fetch, where we use the logs to kind of elaborate our diagram generated by Zipkin. What are annotation? Annotation helps to explain latency with timestamp. They are often a code like server received, client sent, and so on and so forth. Binary annotations are nice because they tag a span with a context, and they are usually to support query or aggregation. So those queries which you see in the browser here, in the browser where I wrote cache.miss, there you can use, for example, http.path to query some relevant spans. They are repeatable, and they can vary on the host, which means that they can have a different value on the client and the server. So for example, you have URL rewriting enable on the server. So the HTTP path will be different for client and different for the server. A question which generally comes in the mind is, can we have a large span? Well, the answer is, it is not recommended. Why? Because it decreases the usability of the tracing system, and also it increases the cost of tracing system. One thing which we should really be aware is of clock skew. Clock ticks at a different rate. And in a distributed world, if our clocks are not synchronized in a way, then all the data that you saw that was gathered and represented by Zipkin is not going to help you to address and resolve those problems. What you can do is you can use NTP, which is, or maybe have some GPS installed in your data warehouse to make sure that that all of your services agree on same duration of time. What is a tracer? Tracer does the most heavy lifting. It is the one which takes care of data propagation, context generation, passing info throughout your spans. Sampling is how we can control how much data we want to record. So if you have a high traffic, like really high traffic, then small fraction of these spans are enough to give you an idea what is going wrong in your system. Why? Because if there is something going wrong and you have a high traffic, then it doesn't really make sense to record all those spans, because the problem is going to repeat itself. That's why a small sampling rate can help us. On the contrary, if you have low traffic system, you have to come out and adjust it based on your needs. But don't make it too aggressive, because if you make sampling too aggressive and start to log everything, then it is eventually going to slow you down, because those things have to written in your DB, and somewhere you will end up accessing the disk. Note that if you want to debug some request, and doesn't matter what this request have to be recorded, doesn't matter what is the sampling rate, you can use a debug flag supported by Zipkin, and these spans which have this flag enabled, they are going to be recorded no matter what the sampling rate is. What is open tracing? Open tracing helps to standardize tracing. It provides vendor neutral tracing API. The implementation is currently available in 6 languages, and you can go and read the documentation for more details if you are interested in open tracing. Spring Cloud Sleuth brings distributed tracing to Spring. It supports Hystrix, async, REST template, Spring integration, and much more. So thanks to this, if you are using and building applications using Spring, then Spring Cloud Sleuth, just add it as your dependency, and you have distributed tracing working out of the box. So basically, it has support for Zipkin. Now I would like to show you the code which I used to build this application, and just to give you an idea how much work is involved in order to build such application. So here I have a catalog service. It really doesn't matter which language I'm using. Maybe some of you are comfortable with Java, but maybe some of you are not comfortable with Java, but the concept remains the same in various programming languages. So what I have here a method called create catalog. So this is the endpoint which get invoked when I issue some request to localhost 8060/ some product ID. And what I do is I can log some event here, like price fetch, product fetch, and email send, which you saw in Zipkin. But under the hood, it's really very simple. I have a get price, and when I call the get price, I create a new trace command here, thanks to which I can then invoke fetch price. And fetch price is nothing but making another REST call to some endpoint and fetching some price from this class. The price is fetched by, if I remember correctly, by price service. And when I was calculating the cost, so here I'm first checking whether I have it in cache. If it is if it is in cache, I return the price. Otherwise, this is for demo purpose. I just add a check here that if the ID is less than 100, then add the value cluster 1 or cluster 2. But if you are running it on a production, you can have here your own logic to decide what type of log or tags you want to create. Coming back to the code, in the same way I can fetch the products here. And this is how I am just simulating a GC post, but what is important here is that tracer this method is supported by Spring. It is not something like standard in tracing that you can call tracer.getCurrentSpan. But usually what you need is you need to get the current span, the one which is created by Zipkin, or you can create it manually if you want to, and then you can log the event there, or you can log some tag, some key value pair there. Another service which I used here is created in Go, just to show you how it works. All right, so again, I don't know how many of you are comfortable with Go, but here I'm showing you that the request was initially made to a Java service, and then we end up calling another service or microservice, how you will like to call. This is not a microservice application because I wanted to keep out all the extra bit out from the code. But it is a service which is written in non-JVM language. So what happened here is Zipkin have support for various languages, and Open Tracing also currently supports 6 languages. I can create a span from the request, and if you want to create the span from the request, what you do is you have to extract from the header the carrier, and the carrier is the one which carries the tracing state. I am extracting this info from the HTTP header, and once I have this info, I am checking if there is no error during the extraction, then create a new span. Here I'm starting a span, or continue another span and create just a child span for it. So this is how we can create by ourselves, not relying on some third-party framework like Spring or open source framework. So if you don't have that framework available for you, you can just see how simple it is to create those spans and start them. And also once I have this, I can create here my parent span, but what is important here is that every span supports some operation, and the operation have a start time and end time. So if you are starting a span, then you should kind of take the responsibility of stopping the span sometime in the future. So what I'm using here is I'm using just some Go syntax, which means I'm using a defer. I'm deferring the call for closing the span, which means that once I will exit this function, this call should be made for sure. It is like finally call in JVM or in non-JVM languages. You can just make sure that once you exit the function, you are closing the span. Otherwise, nothing is going to be recorded for you. Oh, and one more important thing is you can set manually some tags using set tag, and you can provide the key and the value here. And this can be any string which you want to be, which makes sense in your case. And also, if you want, you can also set the types of the span. So here I'm setting, for example, for MongoDB, I'm setting it as a type of span as resource here. So you can use ext.spankind.set. So back to the presentation. So you may ask, well, who uses open tracing or who uses, to be more specific, Zipkin? Well, there are a bunch of big player and medium player and small companies which are adopting to use, which deals with distributed systems, are using it. Twitter, Google, some companies like Facebook, Lyft, and you can read, or you can read there more about it. And also some of them have their own solutions. So for example, some of them, rather than opting to use Zipkin, they want to create their own tracing solutions. For example, here, a company called Uber, they use Jagger as initial version of their tracing system, and now they are merging more and more towards open tracing. You can also use Zipkin with Prometheus, and it exposes some endpoint, and you can configure Prometheus to just get the data from that endpoint. Also, some of you who use Hocula from Red Hat, it also has support for Zipkin. And currently, the Zipkin is available for various languages like JavaScript, Java, Python, and so on. And the last thing which I would like to say is that we should remember that latency is never zero. So rather than trying to run from it, we should embrace it. And distributed systems are really hard to reason because of the distributed nature involved in it. They can have a complex call graph, and also distributed tracing can help to analyze end-to-end latency and understanding the call graphs. Moreover, instrumentation is a tricky thing to do, because when you are instrumenting some code, you have to make sure that you are passing the information correctly across various thread pools or callbacks, or if you are doing asynchronous calls. OpenZipkin provides open source tracing solution for us. It visualizes the request flow. Spring Cloud Sleuth brings tracing to Spring World, and open tracing attempts to standardize the tracing. So thanks for your attention, and if you have any question, they are welcome. So maybe no questions? All right. So thanks a lot. All right, there is a question.
From what you said, it seems to be that instrumentation has to be done manually all the time, but it's probably not always the case, right? You have means how to do it in a simple way, that I don't have to put that piece of code in every HTTP request handler, and that it's possible to trace also applications whose developers haven't designed it for being traced.
All right. So the question, I will repeat the question. So the question is whether it is possible to do some sort of, whether we can do manual instrumentation or whether we can rely on instrumentation out of the box. And second, can we trace those applications which are in which the developers have done nothing about instrumentation or distributed tracing at all? So the answer is yes. Out of the box, if you kind of take the Zipkin and just use it, you have instrumentation out of the box. You have to do nothing to do kind of make it work for yourself apart from adjusting the sampling rate. And in reality, all the code which I show you, I was not doing any instrumentation there by myself. I was just using some open source libraries to add some more specific details which I wanted to show you, that how you can kind of do things not only out of the box, but when you have, let's say, to add some more custom fields to you. But if you don't want to add any custom fields like cache miss or something, all you want is that the request comes and you receive it and you visualize it, and you are interested that which services were touched and which endpoints were invoked and how much time they take. Yeah, just, you can rely on OpenZipkin to do it for you. And the second question of the second part of your question was whether how to do it for the applications which are not using, in which the developers have done nothing about distributed tracing at all. So the question is, it depends. If it is a JVM based application, so what you have to do is you have to just put, and if it is using Spring, you just put Spring Cloud, Spring Cloud Sleuth as the dependency on the during the runtime and the application, and if you redeploy the application, then automatically it will start to kind of gather all those traces for you. Spring Cloud Boot will depend it at the runtime and do it for you. But if it is a non-JVM based solution, or you have your service is written in non-JVM language, then you have to kind of make sure. All right. So you have to make sure to add the necessary bits there in order to trace your application. For example, in Golang, I haven't done tracing in Python or something, but I have done in Golang. So in Go, you have to, the minimum thing which you have to do is you have to create a tracer and use it, or maybe with OpenZipkin do it in a different way. But you have to do a minimalistic thing to able for your application to detect that there is some tracing library available. But all the spans and all the data and all the calculation of time is taken care by OpenZipkin, and it try to kind of put as much information as possible so that you don't have to write it by yourself. Some more question?
I saw that you are using Apache for data Spark.
Yeah.
Have you done any tracing?
Oh yeah, so there is a project called htrace, which you can use. So basically tracing for Hadoop or some clusters. So if we are going towards this direction, yeah, there is a separate. So the question is that, sorry, I will repeat the question. So the question is how the tracing looks like for a solution like Apache Spark or to be more to generalize this question more about machine learning solutions or like Hadoop or maybe Hadoop, which do some batch processing. So yeah, there is a separate dedicated project also there. I used it to do this. It is also open source, and we can use htrace to do this. And I haven't faced any problem yet. And especially if you have your jobs, let's say, are executed on large number of clusters, then maybe sometimes the disk is too slow or I don't know, the network was drop off sometime, and it's really able to detect all those things. And it's also open source, and you can find it online. More questions? All right, so once again, thanks.
Your name is mangled on DevConf website. It's Nahu.
Something odd.
Yes, and I was like, oh, what's the guy? Like, oh, about this, and then I clicked like the presenter, and oh, Nahu, like Nahu.
trying to make sure that I'm not missing it.